We are on to 7.5 scalar and vector projections. So just a little recall, what you're going to need for this section is the dot product from 7.3, 7.4, whether it's with algebraic vectors or geometric vectors. This right here is the dot product. So if we want to find the dot product between vector x and vector y, we have to multiply the magnitude of vector x by the magnitude of vector y, and we're going to get, multiply it by cos theta. Okay, so let's take a look at what a projection is, first of all, visually. So these right here are three scenarios of projection. So if this is vector B and this is vector A, and we're looking for the scalar projection of A onto B, we're looking for this projection, this vector. If I put a light on top of here, let's say this blue marker was a light, it's projecting vector A onto B. So you're extracting the component from A that is in the direction of B. So that blue line right there, that blue vector, this is the scalar projection of A onto B. And if you look at this diagram, we can actually just find this blue line using simple trigonometry, right? We can say that cos of theta is adjacent over hypotenuse. So that's vector ON over vector A. And we can rearrange this, right? We can say, the magnitude, sorry. We can say that, well, I can multiply and find vector ON, which is the scalar projection. And this is just vector A, its magnitude, times cos theta. So these two things. And take a look at what this is. So if I'm looking for the scalar projection of A onto B, I could just rearrange the dot product formula to find what that actual vector ON is. And I can use the substitution here to figure that out. So I can make a little note here and say, well, the scalar projection of A onto B is A dot B over the magnitude of vector B. And this makes sense because if I set these equal to each other, for instance, and multiply by B, I'm going to get the dot product up there. So it's just kind of rearranging the dot product. But really, the best way to understand it is it's really just regular cosine, right? This is just the adjacent. We're using trig to find that side length. And take a look at a scenario like this where I'm going in the opposite direction. So if vector A is actually pulling vector B in its opposite direction, that makes sense because if I'm finding this projection, this ON, my angle is going to be greater than 90. And if my angle is greater than 90, we know cos is going to cause a negative result. So it's really pulling vector B in the opposite direction. So it's kind of the opposite vector of B, right? And its magnitude is going to be of that length using this formula. Naturally, if we have a right angle and I project something down onto A, there's no projection, right? This is 0 because cos of 90 is 0. Okay, so these are the three scenarios of vector projections of A onto B. You could do B onto A, but really it's isolating a component of a vector in terms of another vector. Not horizontal, not vertical, in terms of another vector. So our first example is going to be for two vectors. We're just going to find two scalar projections, frontwards and backwards. So for the vectors A and B, we want to calculate each scalar projection. So just a reminder that these are scalar projections. There's no direction really involved. Okay, they're just magnitudes. So if I want to find the scalar projection of A onto B, I can use the formula that I just had on the previous screen. This is the dot product of A dot B, and this is going to be over the magnitude of B. Okay, so this is going to be equal to, I can say -3 times -2, sorry, that's times, plus 4 times 2, and plus 5 root 3 times -1. Okay, so remember, dot product just this times this, this times this, this times this. Pretty easy. This is my numerator over the magnitude of B. So that's just 4 plus 4 plus 1. Okay, I'm going to say that one more time. 4 plus 4 plus 1 is 9. The square root of that is 3. Okay, so again, I'm just doing magnitude of a vector. I'm just skipping that step here. Okay, so I can say that A dot B over the magnitude of B. If I slap that into my calculator, I'm going to get 1.78. I can show one more step here. and this is going to be 1.78. So the dot product, sorry, the projection is 1.78, but there's another side to this equation that I didn't really write down here, but we had it on the other screen, and that's going to be the magnitude of A cos theta. Sorry, these two are equal. So I can say that the magnitude of A cos theta is 1.78. This is kind of more of a definition of a projection, right? Because we were looking at that blue vector, which was just A cos theta. Okay, so this is my answer. Okay, I like writing it like this because if I have to find the angle or if I have to find the magnitude given the angle, I can rearrange this and kind of go from here, right? Or I can rearrange the formula earlier, like we'll see later on, and we can work from there. Let's take a look at the opposite, B onto A. Okay, the formula is going to be kind of similar. It's still going to be A dot B. But now instead, I'm going to be multiplying by the dividing by the magnitude of A. Okay, so I'm going to get 5.34. I'm not going to do that work again. It's the same dot product. But this time, I'm dividing it by 10. Okay, I have 9. So negative 3 squared is 9, plus 16, plus 5 root 3 squared, which is 25 times 3. Okay, and that's going to give me 100. Square root 100 is 10. So I can say that B cos theta is equal to 0.53. Okay, so the projection of B onto vector A is going to be 0.53 in terms of the magnitude of that vector. Again, we don't know the direction yet, but that's where we're going to kind of get to next. Okay, now vector projections of A onto B, it's kind of the same thing, and this is where unit vectors really come clutch, because a unit vector is just a multiple of 1, but it feeds the information of that direction. Okay, even if we don't know what the direction is, we just say, well, if I is going in this direction, we're just going to multiply it by some sort of multiple of 1i kind of thing. But that'll be more clear as I write this down right here. Okay, so all we do is take the scalar projection. So I'm going to write down the scalar projection, which we just did. This is just A dot B over the magnitude of B. And we want to multiply it by the unit vector. And, I could have done a little recall of a unit vector, but a unit vector is just vector B divided by vector B's magnitude. Okay, this is a unit vector right here. Write that down. And now I can just simplify this and say, well, this is just A dot B over the magnitude of B squared. Okay, and this entire thing is just times B. Okay, it's just a different way of writing this. I wanted to square those magnitudes up because, I'm finding the square root. So if I'm finding the square root and squaring it, that doesn't make sense. I'm just going to kind of do both at the same time. Okay, so let's see how that looks. We have to find the projection of 2, and I don't have a value of OA here, so let me just slap that in. There we go. Okay, so I'm going to use my formula if I want to find the vector projection of vector OA onto vector OB. So I'm going to say that the new vector, we can call it whatever we want, ON, is equal to OA dot OB over OB squared times OB. And I'm going to run out of space here, so I'm going to try to save some time and work. So this is just for 3 dot for negative 1 over 17. And this entire thing is going to be multiplied by 4 negative 1. Again, if this was a geometric vector, vector OA we would have here, right? So the dot product would look a little bit differently, but these are algebraic, they have coordinates. So we're just going to do the dot product like we normally do, 16 plus negative 3. Okay, so 16 plus negative 3, I'm going to take it here. This is going to be 13 over 17 times 4 negative 1. So you can think of this as a scalar times this vector, and this is just going to be 52 over 17, negative 3, 17. And this is, I don't have space to write it there, but this is that vector, the vector projection of OA onto OB. So if I have OA, I have OB, whatever this projects onto OB is this vector. Okay, it's kind of cool how all you have to do is multiply it by its unit vector of B, because we're projecting onto B, right? It's going in B's direction, so we have to get the information of vector B. and we multiply it by that value of 1, and it just gives us the correct direction. Okay, so that's vector projections of A onto B. Pretty easy stuff, so don't sleep on it.